Hello, this is your math tutor Elliot. It is exam season, or exam season is coming up for me as an IB diploma candidate. I take the HL version of physics, but I figured looking at the specimen paper for SL would be good review anyways. And I guess I just wanted to do it like protege effect, I should say, kind of doing it out loud, working through the problems so that I get a better understanding from the material, and then someone else can watch it, and hopefully they get one as well. So here we go. Let's begin. Starts with kinematics. It's nice. Okay, so we want to find distance. Okay, and we have a change in speed. Right. So let's name all our variables. It's probably the first thing to do. So u is equal to 16 meters per second. Acceleration is equal to -4 meters per second. You can see because it decelerates, it's in the opposite direction of the speed. That's what that means. And then until it stops. So this means that your final velocity is equal to 0 meters per second. Okay, so there's a handy equation in the data booklet. It says v squared is equal to u squared plus 2as. Okay, you can rearrange. I like doing the algebra, so v squared minus u squared over 2a is equal to s. Right, or you can just plug in your variables. Since I rearranged, I already got that, so I'm going to say s is equal to, well, v squared is 0 meters per second, so this is going to be 0 minus, and then u squared, 16 squared is 256. I don't think IB expects you to know that. You have a calculator for this exam for a reason. And then 2a is going to be -2 times 4, or 2 times -4. Yeah, anyways, and the negative of that. No, not negative that. Sorry. Anyways, -8, because it's 2 times -4. Because this a is equal to -4. 2 times -4 is -8. Anyways, so that should give you 256 over 8, which simplifies to 32, if I'm not wrong. So this is going to be 32 meters, which is entered to C. You check the mark scheme. C is correct. Yeah, let me just, C is correct. So we got one right. Anyways, moving on. So, mass 2 kilograms accelerates at the speed from a speed of 15 meters per second to a speed of 20 meters per second without changing its direction. That just means that these speeds, you can treat them like velocities because they're in the same direction. What is the impulse? Okay, so if you look at your data booklet, impulse is defined as force times a change in time. And a force, you should know, is defined as a change in momentum over a change in time, which means that your J is actually just a change in momentum. This is the actual definition of impulse, but you can also look at it like this. But the definition of impulse is just a change in momentum. Those are the same things. Anyways, so your J is going to be equal to your mass times your final velocity minus your mass times your initial velocity, because it's a change in momentum, which means it's just going to be 2 times 20 minus 15, which simplifies to 10 Newton seconds. C and C. Excellent. So far, so good. Alright. Now we have work. So work, W, and we have a force. Let's call this F. And we have a mass. Let's call this M. And we have from rest to a speed of 5. So this is U is equal to 0 and V is equal to 5. And we'll just, meters per second. Let's be consistent. Okay. What is the work done by the force? Okay, so work is equal to force times displacement. We have a change in velocity. And we can find an acceleration if we want. So remember, F is equal to ma. And this acceleration is useful because we need to determine this displacement like we did in the first problem. Right, so F is equal to ma. That means that A, your acceleration, is actually equal to force divided by mass, which is therefore means it's equal to 8 over 4, which is 2 meters per second per second. Okay, so now we can find our s, or the same equation. So v squared is equal to u squared plus 2as. If you do the rearrangement, you get s is equal to 25 over 2 times acceleration, which is going to be 10, which is going to be 2.5. And now you can just do the simple algebra. 8 times 2.5. Oh, that's 2.8. Sorry, 2.5. And if I'm going a little fast with the math, I'm doing it in my head mostly, and but you can totally use a calculator, so you can get to this point, rearrange for S, and plug in all your variables. I'm kind of expediting that process since I already rearranged over here. But yeah. So 8 times 2.5 is going to be, what is that, 10 times 2, 20? I don't know. Is that wrong? Let's see. 3 is A. 50. 8 times 2.5. Maybe my math is just wrong. Let's see. 2.5 times 4 is going to be, or times 2 is going to be 5. 5 times 4. No, I've got no idea what I did wrong. Let's see. Oh. 2 times... That's what I did wrong. See, maybe I should have plugged in my numbers. So, I'm right here, I'm dividing by this 2s term. And 2 times 2 is 4, not 2.5. I don't know where I got that number from. Okay, I'm going to leave this s as a fraction just because I prefer fractions over decimals. You can totally turn it into a decimal if you want. It's up to you. I don't think IB cares at all. This is 25. Oh, but they do on their on the free response. Anyway, so this is going to simplify into 2 times 25, which is equal to 50, which is the actual correct answer if you check the mark scheme over here. Anyways, sorry. So let's move on after that hiccup. Okay, a person stands in an elevator, a lift. The total mass of the person and the elevator is 800 kilograms. Okay, so let's call that M. The elevator accelerates upward at 2 meters per second. Okay, so acceleration is equal to 2 meters per second squared. And you see you have that diagram right here. IB is ever so helpful with their diagrams. What is the tension in the cable? I suppose that will just be the F net. So it's equal to, oh no, it will be it'll be tension minus mg actually. F net, m times a. So this is going to be mass times the acceleration of 2 meters per second plus mass times gravity is equal to tension. If I'm doing my, if I'm thinking my free body diagram correctly, right? So this is going to be your mg. This dot is going to be your like body, I guess. Body slash elevator. Whoa. Hello? Hello. Okay. Anyways, and then you're gonna have tension going up because something's got to pull it up, right? Anyways, so that just says that there's tension going up and there's mass times gravity going down, which is your weight, and then your F net, your total force, is going to be the resultant, the net of those two, right? Which is just mass times acceleration. Again, Newton's second law. Newton, goat. He carries physics. Anyways, despite the Newton plug, let's just plug in our values now. So this is going to be 800 times 2 plus, I'm going to say about 10 is equal to tension. You can definitely get I think this is a calculator allowed exam. I mean, now that I'm thinking about it, I should probably read. Is required. Okay, so you can use a calculator on this exam, but this is 800 times 12, which is, what, 9600? Yeah, which is 9.6 kilonewtons is equal to your tension, which I chose answer D. Let's see if that's correct. Yes, D is correct. If anybody, just to recap how I did that, because I kind of was all over the place, you start with the free body diagram. Let's clean up this a little bit. Sorry, Newton. You clean up, you have your free body, your body, right? And you draw the free body diagram. That's all you're doing. So you got to go down with mass times gravity, right? You got weight pulling you down. But you know it's accelerating, so there has to be this upward force, and we're calling it tension. It's the tension in the cable. The cable is actually pulling up on the box, right? And then that's going to give way to a resultant force, which is, again, Newton's second law, mass times acceleration. And so you just have to know that your net force, kind of by definition, is equal to your upwards, whatever direction you declare upwards is. So if I'm saying tension is up and gravity is down, then it's going to be tension minus gravity. And then you rearrange and you get 9.6 kilonewtons. Okay, an object at rest from a vacuum at height h above Earth's surface. Okay, so it's falling, or it's in a vacuum, it's just kind of there. Oh, and now it falls to a point 3/4 h above the surface. So you need to know, so this problem is made easy by one fact. I don't even know if you can solve it the other way, but you need to know that your change in energy is 0, which means that your energy initial is equal to your energy final. Okay? Right now, I'm going to say energy, or now I need to know, energy initial is actually just equal to mg and then h, right? But your energy final is going to be equal to kinetic energy, because it's moving because it's falling, and it wasn't moving before, remember, it's at rest, plus mg times, not 4, sorry. And again, I like fractions, but I know most people like decimals, so I'll leave it at 0.75 h. Right? So now, the kinetic energy. Okay, so remember these two are the same. So you can say mgh is equal to your kinetic energy plus 0.75 mgh. And if you can do subtraction, you know that this is 0.25 mgh is equal to k. Oh, sorry, I'm using a lowercase h. Let me change to capital H, right? So now you know what your k is. And it says just divide that by your initial gravitational potential energy, which is, again, just mgh, boom, boom, this ratio. Oh, let me erase this, sorry. This ratio, I'm going to call it R, is equal to 1 over 4, because it's just 0.25 over 1, which is B. Correct. See, now you got at least 5 marks on your IB exam so far. Okay. This is kind of taking a while, so let me see if I can speed it up. Or actually, you know what, I don't care. It's got weight W, and it sits on a rope in its midpoint. It's negligible mass. Okay, the tension in the rope is... Oh, this is interesting. Okay. So this weight is going to go down like this, and you're going to have tension 1, tension 2. Okay. Is almost horizontal and has negligible mass. Okay. See, this is a problem that I don't really know how to approach. If I had to guess, I'd say it's equal to W2, but it's never really that simple. Let's see. D. Alright, so let's see. The answer is greater than W. See, even I would need help on this one. I don't really know why. I'll review that question later. But for now, let's go on so this video doesn't get too long. Internal energy of a real gas is... man, this is a definition question. You see they moved on to B. So you see this was all A, and now they're going on to theme B. It's all the kinetic and potential energies of the actual particles, if I recall correctly. So I think this is part of it, this is part of it, but this is all of it. So I'm going to say D. So 7D. Alright, correct. So we got this one. I got that one wrong. Okay, so the temperature is 600 kilograms, or kilograms, oh my gosh, Kelvin, sorry. Intensity units are arbitrary, okay. What is the radiation curve of the same object at 450K? So, there's an equation that says temperature times lambda max, which is wavelength max, is equal to some constant. It's like 2.9 something 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 times 10 to the something something something. Anyways, it just says that temperature is inversely proportional to wavelength max, which means that if the temperature decreased, which it did in this example, so if temperature decreased, oh, that's a really bad down arrow, that if temperature decreased, then that implies that wavelength max increased. Alright, so we have a graph that's like this, and it should be by a similar margin, so it's at 1. Okay, so first, okay, so original is in the dashed line, so this is wrong, and this is wrong. Oh, and you see the difference here is that they both increased, but this one has a different location of its peak. Now, I'm sure that there's a way to know this, but my hunch just says C is right, and I could be totally wrong. Let's see. 8 is A. Oh my gosh, I was so wrong. Huh. Maybe I misunderstood this. Let me think about it for a little bit. Okay, so that wasn't wrong. The temperature is inversely, oh, that's, okay, sorry. So the temperature is inversely proportional. That relationship was right, which should just mean, now that I'm actually thinking about it, this location is actually going to move over this way, because you see this is the wavelength axis. See, pay attention to your graph, guys. Okay, so now we can delete that. Oh, that's not what I meant to do. This is still up here. Boom. This is still up here. Actually, so those are all wrong, and A is the only answer. So you see, I did it wrong the first time, but I got there somehow. And B for just thermal particulate nature matter. Not B is not the answer. B is the theme. Okay, so there you go. So just to recap, there's a relationship that in the data booklet that says this times that is equal to some number, which means that this is inversely proportional to that. Okay, and you see that this decreased, so temperature decreased, and if temperature decreased, then that implies that wavelength has to increase because they're inversely proportional, right? Max wavelength, right? And you see that means that because this is the wavelength axis, this maximum point has to occur at a later time, right? Which only happened in graph A. Moving on. Okay, star X has a luminosity L and an apparent brightness B. Star X has a distance of Earth D. Okay, has same brightness. Okay, so Bx is equal to By. Interesting. But is 4 times more luminous. Okay, what is the distance of star Y from Earth? Okay, so Bx is equal, this is in your data booklet, is equal to L, and we're going to use just L. So technically B is equal to L over 4 pi d squared. 4 pi d squared. And there's a whole derivation for this formula, but this is in your data booklet, and this is all you really need to know. Okay, all right. And now you know that it's also equal to 4 times more luminous, which means so it's equal to 4L over 4 pi, and then I put parentheses, and I'm going to call this k d squared, where kd is the distance of star y, where k is just some constant that tells you how much you need to multiply the distance that x is in order to get the distance that y is. Okay, so now you can set these equal to each other, right? So L over 4 pi d squared is equal to, and this is going to simplify, so L over k squared pi d squared. You see? Oh, look at this. The L's cancel, the d squareds cancel, the pi's cancel. It just leaves 1 over 4 is equal to 1 over k squared, which means k is equal to 2, and kd is equal to dy, which means dy, the number you're looking for, is actually 2d, which is answer choice B, which is correct. Okay, 4 identical resistors, each resistance R, are connected as shown. Solid. What is the effective resistance between points P and Q? No idea. There's one resistor here. Oh, maybe I have an idea. Alright, so we can consider this like they're in parallel. So Q wants to get to P, right? And there's one way of doing that, which is like this, where it has one resistor. And there's another way that has 3 resistors. Okay, so it's got 2 real paths. And resistance in parallel, and because it's got multiple paths, so this is the first thing, so multiple paths. Therefore, parallel. Alright, so this is in B5, if I remember correctly. I'm flipping through my data booklet here. And so you just need to calculate the parallel resistance. So resistance in parallel, or 1 over the resistance in parallel, is equal to the sum of the reciprocals of the resistance. So it's going to be, but this is in one line, so this is series. And in series, resistance adds, right? Yeah. So that means that the resistance, so I'm going to call this RS for resistance of the series, is equal to 3R, right? Therefore, this whole relationship of the reciprocal of the resistances, so 1 over R parallel, is equal to 1 over R for this one, and then plus 1 over 3R for this one, the RS. Oh, that's a really bad check mark. Okay. And so you can just take the inverse of this, which means R parallel is going to be equal to 1 over R plus 1 over 3R, which is going to simplify into 1 over, what is that going to be? 3 plus 1, yeah, let's see, so let's multiply this bottom and this top by 3. Alright, so this is going to be, or let's do 3R. Okay, so this is going to be 3R over, the R here is going to cancel, it's going to give you 3, and then 3R, this is just plus 1. So this is actually going to be 3/4 R, which is answer choice A. So in this question was 10 is A. Boom, there you go. Okay. Conductor X is connected to a cell of EMF E. Okay. So let's do EMF. I'm going to use a little V for voltage. Power is P, dissipated in X. Okay, and this is a conductor. Twice as long, 2L. Okay. Have negligible internal resistance. Okay. What is the power dissipated in Y? Okay. Well, let's look at our data booklet. Same diameter. Okay. All right. So my mind is going to resistance, right? So the equation that we want to use is P is equal to V squared over R. Okay. But we don't really know what R is, so we have to figure it out. So we have this relationship that says resistivity is equal to resistance times cross-sectional area divided by length. Well, we know that it's the same material, so they have to have identical resistivities, all right? Right? Yeah. Maybe not. Yes. Okay. So they have to have the same resistivity, right? But they're gonna have variable resistances because they have different areas and lengths, right? Or technically the area is the same because it has the same diameter, but the length is different, right? So our initial resistivity is just going to be our starting resistance times the area divided by the length, and then our second resistivity, which is the same, these are equal, just be known, is going to be equal to some multiple. I'm going to use another constant called K times area divided by 2L. Well, if we want these to be the same, then K is equal to 2, and therefore the new resistance 2, is equal to 2 times the initial resistance. Okay, so what is the power dissipated in Y? Okay, well, let us see. Okay, so the power dissipated in Y is going to be equal to, power Y is equal to Vy squared over Ry. Ry is just that second resistance, which is 2 times the resistance. And then Vy is equal to 2e. So this is actually going to be 4e squared over 2r, which is equal to 2e squared over r. But Elliot, we have no idea what e squared over r is. Yes, we do. It says it has a power of 16 watts. This power is equal to e squared over r because this e is our voltage, and this R is this R, right? And we know that equals 16, so this is actually 2 times 16, which is 32. And if that's not the right answer, then I've got no idea what I'm doing. There you go. 11 is C. Okay, moving on. Two containers, X and Y, are filled with an ideal gas at the same pressure. Okay, so equal P. Or that's sum, not equal. So equal P. See, I like to take notes all over my tests. The volume of X is 4 times the volume of Y. The temperature of X is 327 Celsius. The temperature of Y is 27 Celsius. What is the amount of X and the amount of Y? Okay, all right. Well, this is good old PV equals nRT. Okay. If I had to guess, which I do, I am a guessing man. So I'm going to solve for n, therefore, so this shows that n is equal to PV divided by RT. Okay, so we know that, so now I'm going to do n of x is equal to the pressure in x, which is the same, it's just going to be P, times the volume, which is, okay, so is going to be 4 V. So I'm going to say the volume of Y is just called V. So then the volume of X is going to be 4V. Okay, so B times 4V over R times temperature of X at 327. So is going to be T plus 300-ish. But the R that you're given in your data booklet is actually in Kelvin, so we're going to convert this. Which, if you convert it, it's just plus 273. So if we add 273, this is going to be 500, this is going to be 590, 600. So 600 Kelvin. Oh, and would you look at that, if you add this, you get 300 Kelvin. So really, it's not T plus 300. It's times 2 Ty. Okay? And then, so this is going to be equal to, if we simplify, this will just be 2. So this is going to be 2 times PVE over RT, right? Well, if you look at this, remember, we defined V as the volume of Y and T as the temperature of Y. So this is actually just, so Nx is actually going to be equal to 2 times the N of Y, which means if we want to know this, then we do N sub X divided by N sub Y is equal to 2, which is answer choice C, which is the correct answer. Okay, an electromagnetic wave has a wavelength that is about the size diameter of an atom. Oh man, this is, you're supposed to know orders of magnitude, and this is not something I remember. I want to say it's like 10 to the minus 18 meters or something like that, but I could be completely wrong. You do have... Okay, so what are your choices? This is how I would do this. So, you have infrared, visible light, ultraviolet, and X-ray. My bet's on X-ray, but that is a guess, because 10 to the 8 is smaller than gamma rays, which is the smallest. Just FYI, this is on one of the first pages in your data booklet. It gives you a little diagram of the electromagnetic spectrum based on wavelength. So if I had to guess, I'd say X-ray, but I've got no idea, because the size and diameter of an atom is something you should just know. So this is like just no. This is like just no knowledge. All right, what is the answer? It's D. We got it right. When in doubt, atoms are small. Just use common sense. So atoms very small. X-rays very small. Smallest. They are the smallest on this list, so I chose them. That's pretty much that simple. Is that like a good way to answer all your questions? No, but sometimes you're just not going to know some stuff, and that's how it is. Okay. A particle undergoes simple harmonic motion with a period of t. At time t equals 0, the particle is at its equilibrium position. What is t when the particle is at its greatest distance from equilibrium position? So simple harmonic motion. So it means, like, if you do like a pendulum, so it's going to start in its displaced position. It's going to go here, 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 here. Okay, so that's one period. So this is 1t. Let me make that look like a number. Okay. So you're saying that it starts over here, and what is it? Its greatest distance from equilibrium. So you want to know at this point, which is just going to be one period away. Yeah, or one quarter of a period, right? So it's 1, 2, 3, 4. Yeah. Because if you're at a period, you want to return to the same state that you were in. So it's going to be t over... Oh, that's not even an option. Great, love that. You can also say that it's at t 3 over 4, I believe, because it'll be like over here, 1, 2, and then 3, it'll be over here. So at 3 over 4t. It'll be at another extrema, which is at C, which is correct. I honestly don't know why t over 4 is not an answer. It should be an answer as far as I'm aware, but it may just be that they want it to be a little more complicated than that. You're never gonna get, I can't say never, but you probably won't get t over 8 just because periods come in quarters. If you know anything, and remember, because this is all trigonometry, so sine and cosine, they all come in quarter parts of periods. So you should know that the next important point happens a quarter of a period over. Anyway, so it's C is the long story short. Okay. Oh man, I hate these graphs. Diagram 1 shows a variation of position of the displacement of the wave moving along. Oh, whoopsies. So this is just saying it's a string that's vibrating up and down like this. What is the phase difference between P and Q and the phase difference between R and S? Okay, so here, each of these things is 1, 2, 3, 4, 5, 6, 7, 8. So oh man, I've got no idea. Okay. Position, standing wave formed in a string. Let's go into this. I don't know. My gut is telling me it's going to be one or the other. It's not going to be both. But because I don't know, I'm going to take a guess and we're going to check the answer so we can move on to something I do know so I can't explain it. I don't know. Let's say this one. C. Oh, that was close. It was the only other option. I'll review that one on my own time. Okay, so moving forward. A mass of 0.25 kilograms hangs from spring, with that. What is the natural frequency of oscillation of the system? Wow, I don't remember the term natural frequency. I'm just saying how long does it take to repeat. I'm going to say T, so 1 over T, I guess. Let's check the almighty data booklet. Oh, would you look at that? T is equal to 2 pi times the square root of m over k. That implies that frequency is equal to the square, or I suppose 1 over 2 pi times the square root of k over m, which I don't know off the top of my head. I will use a calculator for that one. Remember, this is your k, and then this is your m. So if you plug it into your calculator, you should get you can probably do this in your head. I got 0.63662. 63662, which is pretty much B. The answer is C. I got it wrong. Do I know why? Not really. Okay, I will check that one out on my own time. See, this is what this is for. Okay. They each carry current. Da, 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 da. Okay, so this is in D now, which hopefully I should be better at than C, because C kind of kicked my butt. Okay, our distance D apart. Okay, so force per unit length. So we were looking for an F over L. Okay, so F over L is going to be equal to mu naught times I1, I2 over 2 pi r. 2, oh, that's a pi, 2 pi r. Okay, so we're going to say we're going to call this F naught over L. Okay, so F naught over L is equal to this, and F1 over L is equal to mu naught is just a constant, and then your I1, and then this is going to be I over 2 over 2 pi times 2r. I'm using r instead of d, but this is so r equals d, because I was just writing down the equation. Okay, so then this is equal to, if we take all the constants out, so I'm going to leave this 2 pi because it was in there, but if we take this out, it's going to be 1 over 4 times what we had earlier, which is F naught over L. On P due to Q after the change. Yeah, okay, so 1 over 4, so I'm going to say B. That's correct. Alright, so we made it up to the next thing. And we're almost done. Okay, planets X and Y orbit the same star. The average distance between planets X and the star is 5 times greater than the average distance between Y and the star. What is the orbital period? Okay, so I want to say that this is a Kepler's law question. So one of them says, I want to say it's t squared is proportional to r cubed. It might be the opposite. Oh, actually it might be, no, I think it's t squared is proportional to r cubed. Where this is the orbital radius. You can prove this using simple harmonic, or not simple harmonic motion, using circular motion, which I'm debating on doing right now. I'll do it if I get this wrong, because then I'll have to do it anyways to know that I'm right. Okay, so orbital period. So you want t sub, we're going to say t sub x over t sub y. And if we square this, then this is going to be equal to r sub x over r sub y cubed. If we assume that this is true, so assume true based on Kepler's law. Well, average distance of x is 5 times y, right? So this ratio, again, I'm going to call it like, oh, I can't use r because I'm using r. Okay, I'm just going to leave it as tx over ty. So tx over ty is then going to be equal to 3/2 of rx over ry. But if you recall, Rx, it says distance between planet X and the star, so Rx is 5 times greater than the average of Y in stars. So Rx is actually equal to 5 Ry, which means that this ratio we're looking for is equal to 5 times Ry divided by Ry, which is just 5 to the 3/2, which is equal to the, oh, sorry, not this cube root, the square root of 5 cubed, it looks like. So D, let's see if I got it wrong. 17. Oh, was 17 the last one I did? Oh, okay, sorry. Okay, so 16 is B. I did not get that one right. 17 is B, and then 18 is D, which I think is what I just saw. Yeah. Okay. You can prove this using circular motion. I might come back to it later, but for now I'm going to keep going. Okay. A charged rod is brought near an initially neutral metal sphere without touching it. When the sphere is grounded, earthed, there's an electric current for a short time from the sphere to the ground. What is the ground connection is then removed? Man, I don't remember. Okay, so let's see. Electrons, direction of conventional current, which means I want to say that electrons are actually going this way. Because conventional current, if I remember correctly, is in the opposite direction of the electron motion. Or the actual motion of the electrons. So that means the electrons want to go up, which means the sphere was positive over here for a time. So relatively positive. See, I will review this on my own time. I've got no idea. I don't even know what the answer is. Let's see. What is the answer? 19. C. Okay. So, charge on the rod was positive, and the charge induced in the sphere was negative at the end. Okay, it was neutral, and it got more positive. Okay, so it should have gotten more negative. That makes sense. So, it was either A or C. Because that's returned to neutrality, right? Actually, I don't know if that's true. I'm kind of making that up. And then the charge on the rod, no idea. Let's move forward. Okay, a positive point charge of magnitude 1 microcoulomb and a point charge of Q are separated by distance D. Okay, electron is placed at a distance from the 1 microcoulomb charge. The electric force in the electron is 0. What is Q? Okay, so F net is equal to 0, which is equal to F positive plus FQ. So this is the positive force that it exerts this way is F positive, and then the force that is exerted this way, which I suppose this force is going to be pulling it because electrons are negative, but Q is going to be negative, pushing it away. Anyways, so that means FQ is equal to negative F positive. And then we can use our handy-dandy little Coulomb's law, which says a constant times charge 1, which is going to be the elementary charge, which is a negative, so this is going to make it negative, times Q, over, where Q is the charge, over the distance squared, which is in this case 4d squared, because it's 2d, quantity squared. 4d squared is equal to negative K E times 1 microcoulomb, which is 1 times 10 to the negative 6, if I believe, over d squared, because that's the only separation there is. If you look at that, negatives cancel, K cancels, E cancels, d squareds cancel. So Q is actually equal to 4 microcoulombs. I should say negative 4 microcoulombs, because, yeah. Because that's be negative to repel it. I must have inserted a negative sign somewhere over here. Like maybe I should have just left them as equal to each other and let Q be the negative differentiator instead of just adding a negative sign. But it is negative. It must be negative if you use common sense. If this charge is positive, then it would pull the electron, which means this one has to be negative to push it away. So it's going to be negative 4 microcoulombs, which is, please tell me I'm 20. Okay, 19, I didn't get this one. But 20 is A, correct. Let me scratch off all the ones I didn't get. Which is, wow, I'm doing okay actually. It's only been like 4. Okay, moving on. What is the sequence for the evolution of main sequence star? We've got 2 solar masses. Man, this is a just no thing, which is my least favorite kind of question. But I doubt that it'll go supernova. And I don't think it's big enough to do a red supergiant, so I'm gonna go B, which is correct. Generally, you need like more mass. So this is like, okay, so you need like big mass to do supernova, and you need like a good bit of mass to go supergiant. So, and 2 solar masses is like obviously greater than the mass of our sun, but is it like much greater? No. So B makes the most sense to me, if I just had to guess, which I do because I don't know the answer. Okay, emission spectrum of an atom. Man, oh, this is E, and E is where I was slacking off. Okay, alright. Well, let's see if I can finish strong. Okay, increasing wavelength. Okay, which wavelength can reduce the spectrum? Okay, well, let's see. I don't know the answer, so I'm going to try and use math to reason it out. So, you have E is equal to HF. Oh, that's not an F, that's a lambda. Okay, F. But F is inversely proportional to wavelength. Therefore, since E is proportional to F, that implies that E is inversely proportional to lambda, to your wavelength. Which means since you have a lot at low energy levels, you actually need high. So this is going to go to high, and then this is going to go to low. So you had a few at high, increasing energy. I'm guessing like maybe something more like this. So I'm going to go C. Oh man, I got it wrong. It's A. I wonder why. Maybe it's because like it's hard to count. Maybe I guess there's like evenish amounts. I don't know. Well, I suppose there's nothing in here, so you can probably count off these two, and then this one by extension. So, okay. By that logic, it has to be A. But you see, I didn't see that, so I got it wrong. I mean, I can change my answer now, but in spirit, I got it wrong. Okay. So this was, I guess this is partially necessary, but really you should recognize that there's some relationship, and they're all at kind of the extreme points on this graph. Okay, 2 radioactive samples, X and Y, have the same half-life, okay? Initially, the ratio of activity of X over activity of Y is 4. What is the ratio after 2 half-lives? Okay. This is the SL paper, and I only remember doing this for HL, so I don't know if I can explain this well. So I guess the important thing to know is that actually, if they have the same half-life, they should decay at the same rate. Which means I suppose the activity should stay the same, which is my guess. So I'm going to say D, which may or may not be wrong. 23 is D. Yeah, okay. So just logically speaking, half-life means that they'll both shrink over time, right? So, which means that their activity will decrease. So, but because they have the same half-life, the margin, so I'm going to say the change in activity for X is going to be the same change in activity for Y, which means that, oh, that's not what I meant to write. Which means that the activity of X over the activity of Y should stay the same. Okay, 3 statements about, okay, heat exchange transfers energy from the fuel rods to the moderator, neutrons, so down neutrons. Which statements? These feel right. I don't know about this one. But I don't even know if that's the 2 and 3 is an option. Okay. This is another just no question, so this is just no. So I don't say C anyways, because that feels right, but it definitely could be D. Oh, look at that, C. Okay. Alright, now for the last question in this section. Okay. What is the radius of X over the radius of Y? Okay, so luminosity is equal to, if we go all the way back to B, is equal to sigma a t to the 4th, and then your area is actually going to be the surface area of a sphere, which is going to be 4 pi r squared. Okay, where this r is actually the distance or the radius, sorry, not distance, the radius of the sphere. Ignore that. Anyways, so that's all to say that this is equal to 4 pi sigma r squared t to the 4th. Okay. So the luminosity is the same. It's important to note they're all on the same line. So Lx is equal to Ly, right? So, but Tx is equal to 4Ty if you check these. Okay, so that means that 4 pi sigma r x squared times 4 t, and I'm just going to say this is, instead of ty equals just capital T, ty to the 4th is equal to that same series of constants times r sub y, oh this looks like an y, sorry, r sub x squared times t to the 4th. Okay, well you see this t is going to cancel with that one. All these constants in the front are going to cancel. And you're just going to get, you can take the square root of both sides. So r sub x times 4 squared is equal to r sub y. Which just means that r sub x over r sub y is actually equal to 1 over 4 squared, which is equal to 1 over 16. Which is answer choice A, which is correct. So, I mean, wasn't great. Overall, I missed 1, 2, 3, 4, and I probably could have gone a little bit faster if I wasn't explaining things, but that's how it is. So, let's see, that was what, 21 out of 25 marks? Let's move on. Let's do paper 1B now. Because this doesn't stop. Okay. Okay, so this is a simple uncertainty question. I probably didn't have to read all that, but this is just to say that your uncertainty in V is going to be equal to the sum of your uncertainties in, I'm going to call this suppliers, which just says it's going to be equal to 0.01 plus 0.01, because I guess it can be assumed, or they're voltage connected in series, so the voltage adds. Oh, my bad. Okay, sorry. So yeah, so V is connected to identical power supplies connected in series. So V adds. So the total V, this one, is equal to the V1 plus V2, because there's two identical power supplies. I'm going to call this S1 and S2. Right? And there's some uncertainty, delta S1 and delta S2, which we know is 0.01 kilovolts, which means that their uncertainties together will add. You can find this at the beginning of your data booklet in the uncertainty section, which just means that your uncertainty in V is just going to be plus or minus 0.02 kilovolts. Which, let's see if I can find that mark scheme over here. Oh, whoopsies. .02 kilovolts. No notes. Okay. T is measured with an electronic stopwatch to the nearest 0.1 seconds. Describe how an uncertainty is T of less than can be achieved using a stopwatch. I guess you can measure. Okay, so you can measure multiple trials together. I.e. 10 trials and divide final time by 10. But it's a 2-mark question, so I feel you have to say two things. But I can't really think of anything else, so I'm going to go check the answer key. Getting time for many bounces and dividing by the... Okay, so that was actually both marks. So I got 2 marks out of that. Okay. The graph of the variation of T with V, the uncertainty of V is not plotted. Outline-wise, it's unlikely that the relationship between T and V is linear. It doesn't look linear. You could be more technical and say like it follows an exponential decay model almost. Like it does not appear linear. I think that's probably all they really care about because it's only 1 mark. Yeah, okay. So I got 0 marks for that. So you need to be more technical. You should say that you cannot draw. So you cannot draw a straight line through all the error bars. So you cannot draw a line through... Oh, my bad. Through all error bars. I guess it just doesn't look like it doesn't count. Okay, calculate the largest fractional uncertainty in T for these data. Like recall correctly, fractional uncertainty is delta T over T. So it looks like the uncertainty is 2 little rungs on this graph, which looks to be 2 out of 4. Okay, sorry, so 2. So it's halfway between, so this is okay, so this right here is going to be 0.5, which means 2 little rungs is going to be 0.1 seconds. So delta T is equal to 0.1 seconds, it looks like, for all these measurements. Oh, but you already knew that. Ha ha ha, that's funny for me. Anyway, so largest fractional uncertainty. So you know that this is some constant, but this is changing. And if this is a constant, then this whole ratio will increase when this decreases, and it will decrease when this increases, because this is, you're dividing by this, right? So if you divide by a bigger number, you get a smaller result, and if you divide by a smaller number, you get a bigger result. So you want to divide by the smallest number because you want to get the largest fractional uncertainty. So you're going to do 0.1 divided by, and then the maximum that you have is this one over here, which is at 1.4, which is going to be 1 over 14, which, did I even do that right? This is 1. Oh, I should actually do a, put that into my calculator, which is 0.7 something, which is 0 or equals 0.0714, which is approximately 0.1. You know, let's see. What am I on right now? 1C, 1A. I'm so confused. T is equal to 0.5. Where are they getting 0.5 from? Oh my gosh, T is on the y-axis. Oh my gosh, I'm so... I was minimizing voltage. No, I wasn't. Wait, am I confused? Okay, so I didn't minimize this. I maximized it. So let's do our math again. We need to get as small as possible, which occurs right here, which is at this line, which is at 0.5, which is equal to 0.2 seconds, or 0.2, not 0.2 seconds. There you go. Oh, and you needed 2, so you need to outline that this is the one you're choosing. T is equal to 0.5 seconds. Okay, alright. We kind of stumbled through that one. I mean, I kind of stumbled through that one, but, you know, we got there eventually. Students suggest the following theoretical relationship between T and V, where A is some constant. To verify this relationship, the variation of T with 1 over V is plotted. Okay? Determine A by drawing the line of best fit. Okay, alright, so let me draw little error bars. I don't know if you need to do this on your exam really, but it's gonna guide me. Oh, well that was kind of... Anyways. Any line that goes through all of your error bars will count as a line of best fit. So let's just call it that. Determine A by drawing the line of best fit. Alright. Then we're going to pick a convenient point. So this is 1 mark will probably come from drawing the line, so we'll count that. And then the next one will be picking points on this line. Alright, so this is a pretty good point, which occurs at 11, 12, 13. Alright, so this is 0.13, and then here is 0.55. Okay, so this is our first point. So P1 is equal to 0.13, 0.55, and then P2 is going to be another convenient point. This one looks good. This is 0.23, and then here 0.95. So 0.23 from a 0.95. right? And because if you think about it, t is equal, oh, that's not, again, not what I meant to do, sorry. If you think about it, t is equal to a times 1 over v. This is going to be the slope of a line of t on 1 over v. So therefore, a is, or we can say is approximately equal to, or you can say equal to, I don't think IB cares, is going to be the change in t over the change in 1 over v, which is going to be equal to 0.95 minus 0.55 over 0.23 minus 0.13, which, if we plug into our calculator, it's going to give us all that divided by 0.1. Okay, it's going to give us about 4. Okay, so let's see, how does that work out? Okay, so that is good. And then I think this is just saying choose your dots like sufficiently far apart, and then it comes out at about 4. Between 3.8 and 4.2 is acceptable. So I think that means we got all 3 marks. Okay, now we're going to move forward. State the units of A. Okay, alright, so this is simple. So remember, A is equal to a change in t over a change in 1 over v, which means that I'm going to say u sub A for units is equal to, I want to say t is measured in what, seconds maybe? Yeah. It's going to be seconds divided by 1 over kilovolts, which means u sub A are equal to kilovolts times seconds, or seconds times kilovolts, which is the truth, or the right answer, maybe not the truth. Okay. Is only affects suggest why, in order to test the relationship like this strength should be much greater than the distance between the plates. Because if it's too small, then the, okay, so if the string is too small, if the string is too small, then what will happen is that it'll be more like a pendulum, right? If it's too small, then it'll be kind of just swinging back and forth between these two plates. And then, which means that there's actually a force of gravity taking effect. So, which is, I'm not going to write it all out, but that's kind of my logic. I don't want to be here too long, taking up too much time, but that's kind of my logic. Be very small. Okay, so the tension is almost balanced by the volt. Okay, all right. So I would have missed this first mark because I didn't mention the tension or the angle. You see, the restoring force of the string, it should be negligibly small. Alright, so I actually would have gotten 0 marks for what I said, which is lovely to know. Alright, now let's go on to question 2. So I got big fat goose egg. Alright, moving forward. Okay, so group A, their estimate is, so I'm just going to talk this one out. I'm getting kind of tired. So group A's estimate, you can see, actually goes to 1 decimal place past this, right? and group B quotes the value at 2.8. So I'm going to calculate this on my calculator, my handy dandy calculator right now. So I'm just going to do 2.7 plus 2.9 plus 3.6 plus 2.7 plus 2.8 plus 2.9. All that divided by 6. This gives me 2.93, which is mean equals 2.93 repeating, right? So if I were to write this, I'd write the mean as 2.9 because you see it's only precise to one decimal place. So you can say that group A included too many decimal places, and then you can see B actually miscalculated the mean because they are correct to the right decimal place, but their numbers actually not correct. It should be like, assuming the uncertainty is somewhere to the 10th place of centimeters, then the correct rounding of this value of 2.933333 repeating forever is rounded to 2.9, not 2.8. So I would say something like that. Let's see. 3 sig figs is inappropriate for A. Rejects trial 3 as outlier. Okay, all right. So you see B did not account for did. You probably should specify the trial as an outlier. I wouldn't have gotten that mark because I didn't specify. So in the future, you should say, talk about exactly where that overestimation came from. Okay. The variation of D with W is shown. Okay, with the weight is shown. Outline one experimental reason why the graph does not go through the origin. I don't know. Let's see. Okay, so they have a ruler, and they put a weight on the ruler to make it bend. And the amount it bends is one experimental reason. Well, because the ruler has I don't even know if it's a ruler, but the meter stick, whatever they're measuring with, plastic ruler. Okay, so the ruler has a weight itself, so it could be deforming on its own. Is one reason possible. Under its own weight. Okay, boom. Gets 1 mark. Or the weight of the pan, whatever they're putting the weight in. Okay. Alright, theory predicts that D is proportional to the weight to the power of x times the length to the power of y divided by e to the I, where e and I are constants. The fundamental units of I are meters to the fourth, and those of e are kilograms per meters per second squared. Calculate x and y. Huh. Okay. What is the length? The length is constant. That's the important part, it would seem. Okay. So length is constant. This seems like it's way more than 2 marks, but okay. Alright, so at 1.0, you get 2. So 1, 2. And then let's see, do you have any other nice points? This 2-1 plays well as well, it would seem. It looks to be about 1, 2, 3, 4, 5. This looks to be about 2, 3.6. Okay. So, So if we divide this equation by itself at a different point, so we say d1 is proportional to weight 1 to the x times L to the y over EI, then we can also say that d2, some different distance, is proportional to some different weight to the x times L to the y over e to the I, or EI, sorry. Then we can divide these two by themselves, and we can say, well, the ratio of d2 to d1 is actually just going to be equal to, because remember, if it's proportional by the same constant. So like terms cancel, so this L to the y over EI, those are all going to cancel, and you're just going to get weight 2 to the x over weight 1 to the x, right? So we can say that, what do we say, 3.6 over 2 is equal to, and you can group this exponent to the x. 3.6 over 2 is equal to 2 over 1. It's going to be 2 to the x, which means that x is equal to the natural log of that divided by the natural log of 2, which I'm just going to say .6 divided by 2, all that divided by the natural log of 2. Okay. So x is equal to 0.848-ish. It's 799 something, so I'm going to say 848. But now I need to figure out what the length to the y, what that y variable is going to be like. I'm not sure, and I don't want to sit here for a while thinking about it. Work leading to x equals, wait, we need units? Wow, okay. Work leading to x equals 1 and y equals 3. Alright, I did not get that. Huh, why? I mean, okay, I guess I can see it's like linear, so maybe it should just be 1. That makes sense. Okay, that's much more simple than what I was doing. So linear, x should equal 1, that makes sense. But even still, are you supposed to use a proportionality to figure out that y equals 3? Interesting. Okay. Alright. I missed both marks on that one. Okay. A ruler has cross-sectional area. Area is equal to A cross B, where A is equal to 28 plus or minus 1 millimeter, and B is equal to 3 plus or minus 0.05 millimeters. Suggestion appropriate measuring instrument for determining B. Okay. I think I saw a microscope on there, but you could also say like a magnifying glass. It's probably fine. I think a magnifying glass in the human eye counts. Definitely the percentage uncertainty of A. So percentage uncertainty, percentage U, is actually equal to 100 times the fractional uncertainty. So this means that what we're looking for, percentage uncertainty in the value of A, is actually going to be equal to 100 times delta A over A. But we know delta A over A, the fractional uncertainty, is actually equal to delta little a over little a plus delta B over little b. So this means that I'm going to call this capital X. So capital X is equal to 100 times delta A, which is 1 over 28, right? Plus 0.05 over 3, which comes out to 100 times 1 over 28 plus 0.05 divided by 3, which is 5.238. 5%. And then you see there it just said 5%, right? Which is correct, right? So what we're going to do here is we're going to say, or we know that uncertainties can only have one sig fig. So uncert only one sig fig, which means that this is actually going to be 5%. And you can see that even these numbers, they don't add up to exactly 5% if you calculate that. They're just rounded to 5% because you can lay one decimal place in your sig fig. Right. That is the physics paper 1 SL, my bad. Physics paper 1 SL run through.